Okay, welcome everyone to this continuation of diagram algebras. Oh my goodness, diagram algebras. Today I would like to tell you about the zoo. There's the famous zoo, the diagram category zoo, the diagram algebra zoo. You remember that's the same. The diagram algebra zoo. Turns out that these people like these things a lot, not just me, some other people as well. And turns out that there's so many, and it is describe type of nice systems. So let's just do it. So there are many of them, and let's talk about it. It's literally the thumbnail of this video. So here are a few of them. So what can you do here? Well, so here's Temperley. So in Temperley, you're allowed to go, well, you're allowed to connect 2 points, either going back or going through, but you're not allowed to cross. This is what's called Brauer, where it's the same, but you can cross. So the difference here is, here you're allowed to cross, here you're not allowed to cross. Okay, cool. Otherwise, we read row-wise. So allowed to cross, not allowed to cross. And here, everything has size 2, meaning I always need connect 2 points. What a difficult word. Connect 2 points. Yeah. So here, always connect 2 points. Here, I'm allowed to connect 2 points. Or no, sorry. Here, I'm allowed to connect 2 points, or just let 1 point be by itself, and I usually just draw this little lollipop to remind myself that this point is by itself, because if I wouldn't do that, it would be some empty, and then it looks weird to me, at least. Some people don't do that, some people just leave it empty. But anyway, so here same picture, right? So here allowed to cross, here not allowed to cross, and here, well, you can either connect 2 things or 1 thing. And here you have no restrictions on how many things you connect. You could connect 3 things or 4 things or whatever. Yeah? You could connect all points together. And here you just get rid of turnbacks. Otherwise, it's the same as here. And here you just are only allowed to connect strands from bottom to top. In particular, if you are not allowing crossings, there's not much you can do, and you end up with a trivial thing. So this is the trivial group, or trivial algebra, whatever you want. This guy is called the symmetric group, and we see the other ones in this video. I hope I will discuss all of them. And this is not just everything you can do. So this guy is kind of the big one, and everything else is a sub thing. Yeah, and this guy has many sub things, not just the ones I've drawn. Oh, many. But anyway, it's always the same idea. Yeah. So choose your pictures you allow, and the only thing you need to make sure is that if you multiply 2 pictures together, you stay in the same type of picture system. Yeah? So let's try that actually. So if you only have pictures with 2 or 1 thing, so if you multiply them together, you only get pictures with 2 or 1 thing. Yeah? Similarly here, you allow everything. So if you, of course, just stack it together where something you allow everything, then that seems fine. You just allow everything. If you only allow crossings and you stack them together, you only allow crossings. So these are kind of naturally closed, and that's usually what you want for those diagram categories. Okay, and they're usually called Temperley, Lieb, Brauer, then rook, planar rook, rook, planar rook. This guy is called Motzkin. They're named after people sometimes. This guy is called partition, planar partition. Okay, this is the rook Brauer, well, very strange name, and symmetric group and trivial group. So the most important ones, you don't need to remember all of them. Probably the most important one is Temperley, Lieb. Brauer is very important, partition is very important. That's essentially all you need to know. And that's a nice way of, some people do it the following. They call, whenever you have stops, they call it partial. So this is the partial Temperley, Lieb algebra, right? You have stops, so you call it partial. This is the partial Brauer algebra, you allow stops. This is the partial symmetric group, and this is the, this just has no really any name. We could call it the partial trivial group if you want. And they call things with crossing symmetric. So this is a symmetric case, symmetric group, right? Symmetric Temperley, Lieb if you want. And things without crossings planar. So you could call this the planar Brauer algebra if you want to call this one here the planar Brauer algebra or the planar partition algebra. Big zoom. And it's a lot of fun. It's a lot of fun. Oh my goodness. So literally everything you can do. Let's try this. So what would happen if you would allow to connect 3 things? Well, can you get away just connecting 3 things? Well, no, you can stick another one on top So you can now connect 4 things. You can stick another one on top. You now can connect 5 things. So as soon as you allow 3, you kind of already end up with a full picture anyway. So this is kind of the natural full list. So 1 and 2 stays with itself, but from 3 onwards, you just get everything anyway. So that's why there's no extra step here in between 1 and 2 and everything. Okay, hopefully that makes, in some world, I promise you, in some world it makes some sense. Maybe not in this world, but in some world that makes some sense. Okay, so I already said that. Here's an example of Brauer. So if you do Brauer and you put another Brauer picture on top, you get a Brauer picture. Yeah, so a little bit of Brauer multiplication. So literally Temperley Lieb Brauer partition, right? Temperley Lieb Brauer partition. Temperley Lieb Brauer partition. Okay, cool. In formal words, this is pairings. Yeah, this is pairings with crossings, and this is so people call how many things you can connect a block. Right, so block size of arbs. So this is a block. These 3 form a block. These 4 form a block. This is 1 block. Right, so this is arbitrary block size. This is block size 1 or 2. This is block size 2. Yeah, and so on. So people call that a block. Okay, cool. Block, very simple. Block. Can I zoom here perfectly? Okay, cool. Where's Temperley? Blocks can connect many points at once, not just pairs. So these are the pair guys. And then you have many, many different things. And here's an example of if you multiply this 2 and 1 picture, you get a 2 and 1 picture. Here another multiplication of a 2 and 1 picture, you get a 2 and 1 picture. And then you still need to decide what to do with the floating components. And for simplicity, we all evaluate them to the same scalar. You don't have to do that, you could be more fancy, but let's just evaluate all of them to the same scalar that we choose beforehand. So here I have 1 internal component, get a delta, I have 3 internal components, I did the delta cubed, you know, and whatever. You can play around with these guys. And there are the many, many different versions. There's not just those on my little funny table here, there are many, many others. And really, they appear like naturally. So kind of the interesting story here is, so maybe we can actually do that live, that they were discovered not just saying, okay, I would like to stack diagrams. No, mathematicians do that as well. But in this case, they were studying different type of objects. So, for example, the Temperley Lieb is essentially an SL2. It's essentially some SL2 picture. And it appeared in, Temperley Lieb is crazy. It appeared in like a 1,000,005 different versions. So in physics, not subfactors, we go through all of them. The Brauer one here from Brauer's paper, it's a classic. It is a classic. Here's Brauer, so multiplying that with that is that. And Brauer really doesn't care how to draw diagrams, so this is a cup. Why not? Right? It really only matters how you connect the points. So these are 2 points connected, whether you draw it like this, or you draw it like that, or you draw it like that, doesn't matter. Yeah, that's kind of nice. You just connect 2 points. And here's a stacking rule, and there's an internal thing, and you just get another scalar. So yeah, Brauer already did that in the 1930s. It's kind of one of the classical examples. And it turns out that this describes orthogonal and symplectic group. Essentially, the cup is a pairing given by the orthogonal or symplectic form that you have. Partition is a bit more difficult. It's essentially the symmetry of the Potts model. But essentially, that's where it comes from. And all the others have some natural appearance as well. So people study them for a reason, because they kind of appear in different contexts. So let's look up Richard Brauer. Richard Brauer, very famous mathematician, has essentially a pioneer of modern group representation theory, or not modern, modular group representation theory, and has done a lot of. Look at those many doctoral students. Was very, very, very active. Publications, Brauer algebra. There you go. The Brauer algebra is that thing here. So here, stack them together. It has a nice dimension. It's 2 minus n double factorial. So double factorial is the most stupid notation ever, probably, because instead of it's a really large factorial, it's actually a really small factorial, because you omit every second step. So 1, 3, 5, 7 instead of 1, 2, 3, 4, 5, 6, 7. Anyway, it has a nice dimension, and it's really nice, and everyone likes it. And it came up under Schur-Weyl duality. So Brauer discovered it under Schur-Weyl duality, which you don't need to understand now, but it essentially comes from orthogonal and symplectic invariance. So that's where this guy comes from. Cool. And nowadays, people go completely crazy with diagram algebras and do whatever they want. So an obvious thing you could try is, instead of having crossings, you take like a braid type thing, or you can put decorations on it, and you can make blocks bigger. You can have whatever. It's so many things you can do, and the whole zoo of diagram algebras is actually really large at this point. Anyway, I hope you enjoyed this video, and I also hope to see you next time.